morning, good afternoon. I'm Denolle, and I will present to you how we're scaling up our big data workflows in seismology using cloud computing. This is a work done in collaborations with amazing grad students and undergrads and collaborators dealing with Excel. Typically, as seismologists, when we want to target large data set, we look at data availability. This is in July, the 16,000 seismic stations that are recording data that we can get a hold of. The IRIS DMC, located in beautiful Seattle, gathers most of that seismic data, and as of early July, it had almost 1 petabyte of seismic data at the center. However, this does not account for the petascale data that is already available for distributed acoustic sensing, so we know that the field is going toward really large-scale computing. Typical data workflow looks like this. We download data on our computer using the internet. We detrend, demean, remove instrumental response, apply some filtering, extract features, all of that is one piece of code that we apply to one file. Now, if we work with different stations or different snapshots, we're going to apply the same code over multiple files, and ideally, we'll have many computers to do that workflow. Now, we can use public resources such as HPC computers to parallelize our flow. So this is the example of the Stampede 2 computer hosted attack in Texas, which you can get a location from Xseed. And you can just establish your parallel download there and then just download the data product or even upload your stuff there. So what would be the utopia for seismologists? A giant petascale seismic archive close to a HPC center. What this computer would look like is a petabyte file system with nicely organized files, tightly connected to a compute cluster and high-performance computing cluster. The cluster is a collection of small nodes that are all tightly connected with InfiniBand. And this will gain nice throughput speeds of above 50 gigabits per second. Now, this is too expensive for NSF to support, and so the community has moved toward cloud computing. Cloud computing is both in terms of storage and of compute. On the storage end, you see on the left a petabyte object store, which I'm using the cartoon and jargon of Amazon AWS, where each of these square here is representing a file or an object. All of them are gathered in a S3 bucket, and each of these can be queried with an HTTP request. The cloud computing part is the same nodes that you would have on an HPC cluster, except that they're not tightly connected. There are slower communication between the nodes. That said, for throughput speeds, this is great. Lots of small computers all can query the object store, and we can gain up to 50 gigabytes per or more throughput speed as we wish. So how do we move data to the cloud? Well, we can use internet, downloading data from IRIS to the cloud. McCarthy et al. Had a great paper in SRL that discussed the scalability of this workflow. They've tested different data volumes and calculated the download time for these on AWS, found that the main limitation is the internet speed. In their exercise, they managed to download and do minimal processing of 6 terabytes of data for just 80 hours of compute time and spend $100. What we brought a different workflow, not in Python this time, but in Julia. And Julian Schmidt was leading this effort, undergraduate student, excellent, who managed to download from the IRIS archive and from the NCEDC archive 63 terabytes of data in 72 hours. And we use a different rate, only spent $50 for this. And so this is a combination of the difference in computing language and some of the data workflows, but nonetheless, this is Julia is great performance for that. And we've dumped all of our data on an S3. We found during this exercise that if you want to crank a lot of data, you want to store your data on S3 for the later compute. But downloading is more efficient with many small instances. We can stream then data from the S3 bucket to your compute. There, the throughput speed is of course enhanced because you have this object store next to you. On a single instance, we managed to get in a US West 2 region 2 gigs per second of throughput speeds with parallel download. Object stores are fantastic for scaling in requests. They can get really hammered with requests. An S3 object can get up to 5,000 requests per second on the single file or object. In my interpretation of the McCarthy paper, the Iris DMC can handle 250 requests per second or so. Once we do this parallel download, we can compute and then dump our data products on the archive again. There's already data available on S3. The SAGE-GAGE bucket has over 100 terabytes of continuous and event data. The temporary array of Poro Tomo has DAS and Denolle array, again, a large data set that can be already queried and hammered for compute and fun science. Now for processing data on the cloud, I mentioned that we do a lot of low memory jobs. And so what we want to do is have this customized hardware where we have memory management and storage management on each of these instances, but we want to be able to launch hundreds of them at once, which you can with this elastic computing platform at least from AWS. And what we can do is query data from several buckets, still with amazing throughput speeds, do all your computing on these instances, and then dump your products on your own S3 bucket, for instance. And this nice heterogeneous computing facility allows to test things like, cost and time. It's always the trade-off. So Tim, graduate students, just finished his PhD, developed a nice ambient noise seismology code in Julia, and tested the autocorrelation of 8,000 channels of a DAS array, recording at 1,000 hertz. And for 1 day of data, he managed to compute all of these correlations in 1 day on the CPU, on a single instance, but only 4 hours on the GPU. And this is the kind of flexibility in the hardware that if you have a bit of money and no time, you spend this GPU, but if you have no money and time, you just go for the CPU. I'll show you a few research examples. The first project I will discuss with you today is the building of a library of ambient noise cross-correlation functions, which we do in collaboration with Greg Barrows at Stanford and his former postdoc Liz and Aurélien. And we call this project the C4, Comprehensive California Cross-Correlations, which we're trying to do is pairing every station pair that you see on this map to create virtual earthquakes and understand surface wave propagation between them. So we're looking at over 700 stations from 1999 until 2021. Each month of our period is a month of data is a good time period to work with a single instance. So on 1 month of data for a single instance, we can gather 30,000 raw waveforms. We've created 60 billion smart cross correlations, which is impractical. So we stacked and downsized to 500,000 cross correlations for past processing. We've run these jobs for each of these months on an R5 instance, and we've tagged on a local storage. It can be an SSD or an HDD. We've tagged on 5 terabytes to handle these, to balance the memory and storage flow. And we, with the codes that we've been using, developed by Julian and Tim, it runs over 5 hours for 1 month of data. So we estimate about $10 per month. Of course, it changes with the availability of stations. So I'll show you a quick example of 1 month stack. This is for the 1 hertz cross correlation. We're looking at almost statewide, but mostly SCS and data. And what we find is for the quite low frequency cross correlation, they're two-sided. You can see a move out, although quite dispersive, but a group move out of 2.5 kilometer per second, which is a nice average of surface wave speed in California. Lesson learned from this experiment, downloading the data only costs $50, as I mentioned. Storing it costs that amount per day. And we had downloaded the entire thing and started doing some benchmarking exercise and debugging, and I ended up paying a ton of money on storage when really I just had to work with a 1 month chunk. So lesson learned, try to avoid storing things in the long run on S3. The second example of research we've been doing on the cloud is led by Tim Clements. It's one of the core of his PhD, using the same data that we collected, the 63 terabytes, plus the 50 terabytes of the SAGE-GAGE. What Tim has been doing is working on a single station correlation, in which case we're doing this cross correlation, but just at one station. Extremely embarrassing parallel at this point. And for the time unit here, we're working with a day worth of data. We're going to collect about 1,000 raw waveforms. We create these cross channels, also cross correlations, but single station. And he's been working with a slightly fancier instances, the M6G in that case, which is more expensive, but also faster. So over the course of these 20-year plus analysis, he's created something like 21 million autocorrelations or single station correlations. And for this unique instance, he computed everything in 48 hours. And we only spent $120. Another common sense thing that we've learned is for some of these low-key post-processing, when you already have all your cross-correlation and you're doing something that does not require parallel processing, you can just bring it back to your laptop and do this on. And so Tim loves working out of his laptop with fancy processing, but only took 4 hours to do all of the post-processing that may take for some other codes a lot more time. So I'll show you what we've achieved with this project is we actually slowly realized that the time series of changes in velocity that we extract from these correlations is turning seismometers into strain meters. And effectively, what I'm showing here is 15 years worth of changes in seismic velocities that we track for each station. For each cross correlation, we can track the change in velocity. And each of these, you can see there's seasonality associated with that, which actually we explain with the elastic undrained response due to precipitation. This is a Southern California example, specifically the Los Angeles area. And what you would notice is that over the course of 15, 20 plus years, there's an increase in the seismic velocities. And this is largely due to the depletion in groundwater level, at least for the water table, of that California is experiencing. And we've done a little bit of seismogeodesy in this other sense. And so here's an example where if you use nonlinear elasticity, you can actually show a proportionality between the seismic velocities and strains, volumetric strains, and that is all somewhat related to the water load. And so we've compared our DV time series flipped axis here for negative up, changes in seismic velocities for a site next to Taran Pass, and compared them directly with groundwater level and estimate from GRACE. We also looked at the GPS time series nearby, but we found great correspondence between seismic velocities and water levels, thermal strains, and all that kind of thing. So that was kind of eye-opening. Thanks to this massive cloud workflow, in a couple of days you can actually come up with strain meter data for 20 years worth of evolution. So now I want to touch a little bit on teaching on the cloud. I found that, with COVID and remote teaching, we found that it was necessary to move to cloud platforms to do some of our tutorials. And I've learned a lot by migrating my homework sets and computing with Python on Google Colab notebooks. To the left, you can see that a quick finals that I gave to a graduate level course where we've I was able to upload some of my own seismic data on a Google Drive, which you can directly mount on the Google Cloud instance by doing some kind of syncing. So it allowed me to upload my own data or metadata, and then the students would just mount my drive to their local instance and run a lot of things, data crunching on the fly. They could also themselves dump some of their results on the Google Drive, which then I could take and analyze for grading. So there's some very fixed hardware and fixed software and environments on Google Cloud with Colab for Python. So we had to think about UpSpy and things like that. But it was extremely successful. And if the Google Education workspace remain active, at least this is still a viable way forward. The second thing I'm trying to evolve a little bit more into is using Binder to construct both controlled environments that we want. It's very specific for, if I want to teach in Julia, or if I want to teach in other environments that the Google Cloud does not have automatically. You can just create your own containerized environment, and I use Binder to launch your notebooks. So we created GitHub repos for our own classes, and then Binderized some of our tutorials, so then the students can directly launch the tutorials from there. Now the hardware behind Binder, I think, is a little bit of distributed server between AWS and Google and maybe others, but I'm glad not to have to be aware of this and just work with that. For bigger teaching requirements, such as machine learning requirements, some of the TensorFlow modules are quite big, and so we want to make sure that we have to think when we set up our Jupyter Hub, like what's the allowed memory. So there's a little bit of thinking to do in that sense, but it's so much easier than having students install the right version of Python. One of the challenges that scientific computing has with cloud infrastructure is the data format. The geospatial community is, I think, caught up with the challenges of the object store type systems and developed the cloud optimized GeoTIFF for imagery. Time series data is a little bit trickier. We want big files, but we want to read very small bits of it. And so NASA is spending a lot of time developing core tools to read H5 formats on the cloud. And JP Dwinsky is a software engineer at NASA who's rewrote the H5 library to optimally read H5 files or bits of the H5 files on S3 through the ISAT2 projects. And this is work that we're doing with Brad Lipovsky and incoming grad students at uni to basically use the ASDF H5 container to read efficiently using ASFash Core on S3. And I just wanted to note that JP Dwinsky is amazing. He's managed to speed up the read times by 130 manifolds to read data on S3 and on local. So it's not rewriting the format, it is rewriting the library that has been successful. So if you're like me, a little bit confused with Docker, EBS, EC2, all that jargon of cloud computing, I still understand it. It's still challenging. We really want to get to the science. And so what we're doing is working with potentially amazing people. Weekend Ju, who's graduating from Stanford, with this nice end-to-end workflow on any cloud. I think he has 2 cloud providers possibilities, where everything is containerized, everything is nicely orchestrated with Kubernetes, and the data streams in. He applies his machine learning modules like face picking and location, and outputs a warning or an alert. So these are end-to-end workflows that will create on the cloud. If we don't want to see what's in the backend, we work with Dylan Mikesel, who was funded by ESIP, to make a web-based API for noise cross-correlation analysis. So in which case, you don't see the backend of the orchestration of what Julia and environment you need. You just see the browser page, which is really going to be a fantastic user-friendly way. We also got almost funded a 4-year project, Scoped, that is led by Cartape, where we are really exciting project to combine the benefits of the cloud for big data, the benefits of HPC for wavefield modeling, in a combined hybrid cyber infrastructure to please everybody. And this will basically provide lots of training to students, benchmark softwares and containers and everything we need to do large-scale seismic data processing. How do we pay for cloud? Credit cards. It's not that expensive except storage, but if you want to rescale things up, you submit a 2-page document attached to your NSF proposal using the Cloud Bank resource. I can provide examples, but the Cloud Bank website has a lot of resources on how to write these correctly. It's the same as an exceed allocation, except that you're turning your compute time into dollar values based on the instance you want to use. I have not addressed in this talk is IoT device sensors streaming to the cloud. There's a Mexican startup that is doing this for early warning. Many communities have adopted the cloud. The geoscience community, more like on climate science and environmental science, is using through PenGeo, is doing a lot of that development. And the SCEDC is leading the way in terms of cloud computing for seismic data, and it's got a lot of cool tutorials for that as well. So I'll leave it up to here. My conclusions are below with some tips, but please contact me if you have any questions.